really matter. I mean, the optimum point will still be the same. Okay, whether we have this pi in front of that or not， 可以吗？就是我们可以先稍微观察一下，因为有时候就是直接观察一下就可以稍微简化问题。Okay, so we can try to simplify problem formulation by some observation. That is, even if over here it is not pi, even if this is 1 in front of this x1 squared x2, it still doesn't really matter, right? When we try to maximize this, yeah, this coefficient doesn't really matter, okay? So, in this way, I think we can simply transform this into a simplified form, and also the standard form, okay? So, yeah, we can redefine the problem, okay? So let's try to redefine. Okay, yeah. We can just do this, minimize negative x1 squared times x2, right? Because when we try to minimize something, it's equivalent to when we try to maximize something, it's equivalent to minimizing something, okay? And I also said that because having this pi or not, yeah, it doesn't matter, right? We can still find the same point. Oh, but when you try to figure out the function value, that is finally when you want to know so exactly what's the maximum value, then you still need to multiply by pi. 可以吗？就是我刚刚说了，你虽然可以稍微简化一下你的问题，就是先不用把 pi 放进去。当然你要放也可以，但是我们就先简化，先不用把拍放进去，但是最后你还是要记得要把这个拍最后再乘进去。就是它找到 x1 x2 的值虽然一样，但是你还是要记得最后要把拍乘进去。还有就是我这边也把它先改成负的，最后要把它改回再乘以负1。Anyways, so let's redefine the problem to be like this. So minimize this subject to the constraint, okay, and let's just call this h. Now h, yeah, of course h is a function of x1 and x2. H is defined as x1 squared plus x1 x2 minus 12 equals 0, okay? And then we can simply define L as negative of that plus lambda times h. Now I'll just say h over here, okay? And then very quickly, I believe we can write down this partial derivative with respect to x1. We have negative 2x1 times x2. Over here we have lambda times 2x1 plus x2. Okay. This is equal to 0. And partial derivative with respect to x2. Negative x1 squared plus lambda times x1 equals 0, okay? And the third equation is just taking partial derivative with respect to lambda, so we will end up with the constraint equation, okay? So we have x1 squared plus x1 x2 minus 12 equals 0, okay? Yep, so now we have the three equations, and we have three variables, so I believe we are able to solve this problem. Okay, now let me check and see whether everything looks good. Yeah, I believe so. Okay. Oh, and by the way, hopefully you remember, when you see equations like these, usually the easiest way is to see whether you can find the equation like something times another, okay? And usually starting from that is the best way to solve the problem, okay? So from here, I believe you can easily see that, oh great, over here we can simplify this as, so now it's like x1 times lambda minus x1 equals 0. Okay, great, yep. So we can rewrite this as this way, okay? and you can see that it's either like we either have x1 being 0 or lambda being equal to x1, right? So it means that x1 equals 0 or x1 equals lambda, right? But if x1 equals 0, then what are we doing? Yeah, then it's nothing, okay? So it doesn't really make sense. So when x1 equals 0, yeah, basically we can just we can discard this kind of possibility, okay? And then we start with x1 being equal to lambda and try to plug in and then try to solve the problem. I think I don't think I need to write down the whole detail, right? You can just start from here, and then finally, let me just give you the solution. Okay, so finally, what we have, okay, yeah, x1 equals 2, x2 equals 4, okay, and yeah, and what is lambda? Yeah, lambda is of course 2. Yeah, lambda is equal to x1. Okay. Yeah. So any question? Yeah, I hope this is now very straightforward. Okay. Right. So from here, yeah, I think this is a very practical problem, right? Suppose you want to build something, and you only have this kind of limited material, okay? Yeah. 也就是说，有点像是折纸好了，你的纸的大小就是这样大，你要想尽办法用你有限的这个纸，然后折出来，最后变成是可以装最多的水好了 ，OK, something like that, OK. So with this limited resources, with fixed surface area, and then you try to maximize the amount of water that you can contain, okay? Yeah, I think it's a very interesting problem. And what we have found is that in this way, if we want to do this, then the best way is to have the height being twice as large as the radius. Or we can say that the diameter should be the same as the height. Okay, yeah, so that's something we can learn from this, okay? Yep. Any question? I hope this is not too bad, okay? What time do we have? Okay. Let's see. Oh, we can also learn something from the. Whoops! I just. Anyways, yeah. Let me write this down one more time. Okay. So from this kind of method, what do we have? Or I think it's better to write this down using vector format, okay? Okay, so in this method, in this kind of Lagrange multiplier method, what we have is this being equal to 0, and what is this? That is gradient f plus lambda gradient h equals 0, okay? So if we use this kind of vector format, is it alright? This means taking partial derivative with respect to each xi， 可以吗？这个 gradient 的意思还记得吗？它就是对每一个 xi 做偏微分，就跟这边一样，对 x1 做偏微分，对 x2 做偏微分。Okay, so basically over here, so in vector form we can just write it down as a zero vector. Okay, that is because L is defined as f plus lambda h. Well, when we have that, it's equal to saying this, okay, gradient f plus lambda gradient h equals 0. So the geometrical meaning or the physical meaning, okay, so the physical meaning is that gradient f is a linear combination of gradient h or negative gradient f, yeah, but that's the same thing, okay. So gradient f is a linear combination of gradient h, gradient h at the optimum point, okay. And there's also something, yeah, another thing that is important. Yeah, I will talk about that in a little bit more detail during the next hour. That is, basically, yeah, it's a linear combination of gradient h, and over here, those gradient h should be linearly independent. Okay, I mean each gradient h should be linearly independent. If not, then there might be a problem, and we may not be able to solve the problem. Okay. So, but anyways, right now, yeah, let's just try to understand this. So, yeah, okay. If you want a figure, okay. So let's say we can use a two-variable example to illustrate the idea. Okay. Let's say f is, so suppose those lines represent the equal value lines, okay, and we try to minimize f subject to some kind of constraints, okay. So let's say, now let's make it simple, okay. So suppose we have okay, let's say maybe we have, oh, wait, it doesn't look that good. Okay, so maybe I'll do it in this way. Yeah, I think I'll just use one constraint to illustrate the idea. Okay. So how about this? Let's just have one constraint. Let's say the constraint is over here. Okay. Yep. And basically over here is my optimum point. Okay. So here is the x star. Okay. So what do we mean by this? This means that gradient f okay. Maybe I should give you guys some values, okay? So let's say we have this kind of problem, minimize f, that is x1 minus 2 squared plus x2 minus 2 squared, okay? Suppose this is my f, and suppose our constraint is like this, x1 plus x2 must be equal to 1, okay? Or minus 1 equals 0. Suppose we have this kind of problem, and as you can see, without the constraint, originally here should be the minimum point, right? At 2, 2, without the constraint. However, with the constraint, this is the optimum point, okay? But anyways, from here, what do we know? What we know is that gradient f, I hope you can see that, basically this is the direction of gradient f, right? Over here f is smaller, but over here f is larger, so gradient f is in the direction of function increase, or actually maximum function increase. 我有跟大家讲这个吗？希望不过应该以前有学过哈。gradient f 的方向就是 function 值增加最大最快的方向。那在这里 function 值应该比较小，在这里这里应该是这里是1 and 1 OK， 好，反正就是往这边只是 gradient f OK and what is gradient h? Gradient h h is this and gradient h okay let's quickly write this down. So h is that. Gradient h is what? It's still 1, 1, okay? So, as you can see, it just means that gradient h and gradient f are in the same direction. And if we have more constraints, then gradient f is a linear combination of gradient h at the upper point. Okay, so I just want to show you the physical meaning or the geometrical meaning of the Lagrange multiplier method. Okay? Yeah. So let's take a break. Okay.